All right, so in this packet from last week, we tackled focus directrix. I'm going to go to this front page and just talk about even and odd functions again. All right, so this has popped up in our review throughout the exams, but I just want to officially cover it. Even functions, so I'm just going to highlight a few things, are symmetric to the y-axis. Okay, so again, if I draw a line at the y-axis, you should see if I fold over that line, they should line on top of each other. Same thing here. So even is symmetric to the y. Odd functions are symmetric to that other O word, the origin, okay, which is a point. So I'm going to highlight my origins here. Okay, what origin means, that symmetry isn't as obvious to some people. What origin means is that if you flip it upside down, it should look exactly the same. Okay, so origin is 180-degree rotation. So I'm just going to make a note, if you rotate 180 degrees, it should look the exact same. But odd goes to origin. So you had to test them just graphically, and then we had to do the algebra test. So the algebra test said you substitute in negative x, and if you got the original, then we said it's even. So it's even if I substitute in negative x and I get out the original. Then we call it even. We said it's odd if you substitute in negative x and you get out negative f of x. You get out the opposite of the original. And then if neither happens, if it's like a mixed match, then we just say neither is true. It's not even or odd. And most things in the world are not even or odd. Okay? If they are in the exam, they made them that way. They made that to happen. So it says classify below here each as even, odd, or neither. So number one, what type of symmetry do we see? Even. We can draw on that line on the y-axis. So we have even symmetry. How about number two? I think, well, can we rule out even for sure? Okay, so look at what this looks like. Here's the origin. I have this little piece above, this big piece below. If I flip that upside down, does that look the exact same? No, so that's definitely a neither. Has neither even or odd symmetry. How about three? Who can we rule out right away? Evens out. If I flip that upside down, does it look the exact same? Yeah, so I think we can definitely go odd there. Okay, so graphical is pretty straightforward. And now we have to apply the rule down here. So this is, again, they throw this in the short answer every now and then. So I want to test. So I'm substituting in negative x for all my x's. And we'll just see what we see. What happens if we cube a negative? Do we get a positive or a negative? Negative. A negative. So this becomes negative 3x cubed. And here I just have a negative times a negative 7, which gets me a positive 7x. So I'm just going to kind of make an arrow. How does that compare? Is it the exact same? No. Is it the complete opposite? Yes. So since it's the complete opposite, opposite's that O word, we say it's odd. Okay. Do the same for the last one. Test to see if that's even, odd, or neither. Yeah. 100%. Unless it said in the direction, if it was short answer and it said algebraically, you'd have to show this. But if it didn't say that word algebraically and it was in short answer, 100%, I would graph it and do the same thing. Great question, Natalie. Eight negatives make a positive. Oops, I missed my two. Two negatives also make a positive. And then I have a positive x. How does that compare to the original? It's neither. The first two are the same, the second two are the same, but the last one changes. So again, this would be a neither. And if you wanted to verify, like Natalie said, you could just graph those and just verify visually what they're symmetric to or not to. Okay, so a quick review of even and odd symmetry. The next page was a review of inverses. Are we good with inverses? Does anyone need inverse review? Switch the x and y and solve for y? I feel like we've done that a lot. Anybody? Same thing, switch the x and y and solve for y. Any question that says inverse, do the same thing. You can go to the inverse or from the inverse. Yep, great question, Sarah. Okay, last little one is end behavior. These are just annoying things. Obviously, you don't see these a ton because we've done like 3 exams now and it hasn't popped up yet, but it pops up every now and then. Sketching the graph of an odd and even degree. So this is different than what we just did. Odd and even degree is different than odd and even function. This is about end behavior. So just as a reminder here, if it's even, that means the end behavior is the same. So I'm going to put same end behavior. That means it starts and ends up, or it starts and ends down, like a parabola, like x squared. So when I think even degree, I think of x squared. They either both start and end up, or if it's a negative x squared, they start and end down. All right, so here's a couple examples. This says it's a degree 2, like an x squared. So the degree is the exponent, degree is 2. That tells me it can have a maximum of 2 roots. So here's an example. This one has 2 roots. And this is a positive leading coefficient because it's ending up. This has a negative leading coefficient because it's ending down. So there's 2 things you're looking for, the degree and the leading coefficient. Here's another example of an even degree, x to the 4th. So the degree is 4. That means it can have a maximum of 4 roots. Okay? If the leading coefficient's positive, it ends up. And again, ending is to the right. It ends up. And because it's even, it has to also start up. Here has 1, 2, 3. Just as a reminder, this is a great example. This one does what when it hits this axis? What is it called? It's a bounce. That means it's a double root. Okay, let's make a note there. That's a double root because of the bounce. This guy is still x to the 4th, so it's going to do the same end behavior, but it has a negative leading coefficient, which means it ends down. Okay, so there's 1, 2, and here's again a bounce, so it has a double root. That's where the 4th is. All right, switching gears to odd degree. Odd degree, the end behavior is the opposite, like in that O word, opposite end behavior. And again, when you think n, think the far right. So let's say we have x cubed. That means I can have 3 roots, a maximum of 3 roots. If the leading coefficient's positive, that means it's going to end high. And because it's an odd number, it's going to do the opposite at the start. So it's going to start low. Okay, odd meaning opposite. If the leading coefficient's negative, that means it's going to end at the right end low, which means if it was opposite, it would have to start high. Now notice this one only has 1 real root. Let's make a note. That's 1 real root. Therefore, it has how many imaginaries? 2 imaginaries because there was a total of 3, a degree 3. Same with this graph. This has 1 real root because you can see it and 2 imaginaries. Okay, imaginaries always come in pairs, so they have to be an even amount. All right, take a look at this one, x to the 5th. The degree is 5, so there could be 5 roots. If the leading coefficient's positive, it's going to end high, which means if it's odd, it's got to start low. And there's 1, 2, 3, 4, 5. And then again, if the leading coefficient's negative, it's going to end low, which it starts high, and you've got your 5 roots. The multiplicity of the root, again, is how many times the root occurs. Remember, if it crosses through, its multiplicity is 1. If it bounces, it has a multiplicity of 2. Okay, so this passes through, oops, where's the x-axis? I just lied. Here's the x-axis. Let's make a note. Here's a root, and it bounces there. So if that root is x minus 1, that factor is x plus 1 squared because of the bounce. Any bounce gets a multiplicity of 2. This one passes through at x equals 2, so x minus 2 just goes to the first power because it passes through. and of course y equals. Okay, bounces have a multiplicity of 2. Let's see what else we can get up here. All right, let's try this one. No way. A cubic with roots -1, 3, and 5. So they want you to graph this. So you have to hit at -1, 3, and 5. So graph your function that hits at -1, 3, and 5. You have to hit at -1, 3, and 5. It's a cubic. So what is that power? X cubic, x cubed. Even or odd degree? Odd. So the end behavior is going to be opposite or same? Opposite. So those are the things we want to keep straight. Odd number, odd degree, opposite, end behavior. Do we know anything about the leading coefficient? No. So all we know is it has to go in opposite direction. So if it's going to end high, that means it has to start low. What's one thing this could do? Where could I go? Okay. I could bounce if I wanted. Could I bounce? I don't think so, because then how would I hit? That means there's 2 roots there, right? And I need to hit 3 separate ones. So I think it's got to go through. That's 1. Go through, go through. So do we understand why it can't bounce here? I can only have 3 roots, the max, so I couldn't bounce on that one. Let's try this one. A negative quartic function with a positive roots at a and b. Okay, so positive roots are a and b. Negative roots are c and d. So we don't know what they are. We're just calling them positive or negative. What does quartic mean? X to the 4th. So what does that tell you about the end behavior? Same or opposite? Same behavior. If the leading coefficient's negative, what does that tell me about the far end? It's got to end down. And because it's even, it also has to start down. Now you go ahead and connect so that you hit those 4 zeros. So I think it's got to look something like this, to that effect. Okay, so just make sure we're clear on the starting and ending. All I want you to do tonight is finish this page here, whatever's not done on this page 25. Okay, bring that exam back tomorrow, this page 25, and I think we'll call it good. Yeah. No. So again, if you plan on doing corrections,